And with that, I'd like to introduce Travis Goodspeed. His title is A 16-Bit Rootkit and Second Generation Zigbee Chips. Take it away.
Howdy. Can everyone hear me? Good. So today I'll be explaining how the access control mechanisms of second generation Zigbee chips work. This will show you how to extract a key from a Zigbee chip so that you can replace its identity on the network. So you grab a board, say an AMI smart meter thermostat. You stick a couple needles into it, you wire a device up to it, and then you debug it. And when you debug it, there are mechanisms in place to keep you from extracting the keys. These mechanisms aren't very effective. Today I'll be talking about two of the more popular chips in particular. I have an unpublished exploit against the third, and the fourth has no protection. So of the 4 vendors that can sell you chips today, they're all broken. They're broken in such a way that I can't really fill an hour lecture describing it, because you'd say, oh God, you're repeating this again, this is boring. So to continue the remainder, I'm doing a sort of double feature where the second half describes how malware will work on these chips. So if you have a firmware image and you wonder whether or not a rootkit has been added, how can you look at it to find out? How can you tell the difference between what might be a weird version of a legitimate firmware image and a hacked firmware image when you don't have access to the source code or to a complete history of all valid versions? These are the chips that we'll be dealing with today, the ChipCon 2430, also the 2431, the 2530. Every ChipCon chip with a 4-digit part number that contains a CPU as well as a radio. We'll also be talking about the Ember EM250 and EM260. These are the only chips in the 200 series, but it applies to all of them, as well as every other chip that uses the XAP2 core that they chose. Update this. Yeah. As far as the rootkit goes, the idea is that topics for today. Yeah. Okay. So as far as the rootkit goes, the idea is to create a very small, very portable operating system and then to shove that into the existing application, so that instead of having just a single application running on the bare metal, you have both that application and a second one, which is monitoring it. And on these platforms, there are a lot of tricks you can use that would never work on a PC. For example, suppose that I want to listen for a command packet that tells me when I'm supposed to, say, execute a command in the rootkit. But at the same time, I don't want to interfere with the proper operation of the network, because I don't want it to be obvious that the device has been tampered with. The device is so small and has so little RAM that it's actually feasible to scan all of memory. Just check every last byte, looking to see if there's a proper packet for you to handle, and if so, you do it. And you can do this repeatedly, and even if you do it too often, the performance impact is minimal. But the reason I'm discussing this is so that you'll have a chance to identify these things. And later in this track, Mike Davis will come up and demonstrate a smart grid exploit of his own, and you can sort of compare the two, seeing how many of these techniques are present there and how many of the identification techniques would identify his worm. Oh, that's my problem. My scroll wheel is changing your view. Okay, so in IT, malware is very common, and every common device has worms for it. You've got viruses affecting Macintosh, Windows, and Linux, and especially on desktop machines, they're very annoying. You have pop-up windows for pornography showing up on your computer at work. You begin to think, hey, maybe there's someone else in the system, and it's not just a fluke. In embedded systems, you don't have a command line, you don't generally have access. You just buy it as a prepackaged product. So the system comes up while simple malware is detected on a PC, on a microcontroller it could sit there for years, and because no one's actually reading the code, no one's actually paying attention to the performance of the system. Anything that's reasonably discrete will go unnoticed, even if it's simple, even if it doesn't obfuscate itself or mix itself in with the legitimate code. So when you find these things in the wild, there's no reason for them to defend against identification in the same way that PC malware would. And it's because of that it's feasible to run through and look at them. Bobby, who's actually in the audience here, was once in a meeting with me, and he kept repeatedly saying the CIA thing, the confidentiality, integrity, availability, that sort of stuff. And then I realized that on these chips, confidentiality is only used to prevent plagiarism, and you're on the wrong slide. So, so all of these access control mechanisms that you'll find on these chips are not intended to prevent keys from being extracted or to prevent an attacker from gaining access to a network. They exist to prevent an attacker from manufacturing an unauthorized clone of a given device, which means that flash memory is often reasonably well protected, and RAM is unprotected. As far as integrity, they only care about accidental corruption. So these chips will go to extreme lengths to make sure that they don't try to write flash memory while a battery is low. But they do nothing to, say, check the rate of an external clock at the time that they write flash memory. And as far as availability goes, they've got a watchdog timer that will just reboot the chip when it crashes. So even a seg fault will often go unnoticed in these things. And there's very rarely a log or anything that you can look back at to figure out what happened. This here is the way that these things implement their security, and that's with warning stickers and tamper alarms to prevent you from opening them up. This is from an electric meter in Tallahassee. And once you get inside, sometimes they have defense mechanisms, but you can't afford to do that on consumer-level Zigbee devices. So even if you do it for your electric meter, you'll never do it for your thermostat. In military applications, how the hell would a physical tamper device work on a cluster bomb? I mean, if you've got millions of these things dropping out and they all have to communicate with each other, it's not feasible to check to make sure that they're not tampered with in the air. And it only takes tampering one of them to get the keys to participate in the network from which you can begin to launch traditional IT attacks. So these chips are used for smart meters, they're used for landmines, they're used for all sorts of wireless networks, and the cryptography of these chips is trusted to protect their networking protocols, which might not be so trustworthy. Some of them have optional passwords, some of them have Stack Overflows. They're not audited in the same way that PC server software is, because on a server, you have the entire world accessing you, the entire world looking at you, and the entire world can fuzz you, or purchase your product, throw it into an emulator, and begin to debug it. So of the three topics for today, the EM250 has no protection whatsoever. If you plug up to it with a JTAG debugger, which you can purchase from the manufacturer, you ask it politely for all of its firmware, all of its keys, and you get it. I'm looking at repairing these with a stun gun or another high voltage source to actually blow out the debugging pins, but I haven't had much luck with that yet. As far as the ChipCon radios go, and I'm referring to the second generation chips, not to the first. The first generation chips had another vulnerability that we'll go over in a minute. But on the second generation, the firmware is reasonably well protected while the keys are not. Everything in RAM is exposed, and I'll explain later, every key is copied into RAM by default because of a behavior in the C compiler. If you're using this chip in a commercial product or in anything else where you care about security, you can actually change your firmware to lessen this vulnerability. and I'll cover how and why later. A more detailed explanation of that is in the paper that you'll find on your Black Hat CD. So a couple of disclaimers. The Ember 300 series, which is yet to be released, will be better than the Ember 200 series. They're switching to an ARM Cortex M3 core, and they're adding, this core includes access control mechanisms in the form of values stored in flash memory. The ChipCon radios are being replaced by the ChipCon 430, which is based upon the MSP430 microcontroller by Texas Instruments, who owns ChipCon, instead of the Intel 8051 clone that's in the prior ChipCon radios. And then as far as the MSP430 worm goes, I chose it for a concrete example. I'm not discussing any particular vulnerability to exploitation on the MSP430 today. Instead, I'm discussing what the payload of that vulnerability would look like. So microcontrollers themselves are just little computers. You've got 8 or 16-bit registers. They're of two types, either von Neumann or Harvard. Von Neumann is how your PC presents itself to the running application, in that you have one memory, you have a pointer as an address. If you resolve that address, you get some data or you get some code, but whether you get data or code depends upon where the address points. On a Harvard chip, it's not the same. You have two memories, one for code and one for data. And a pointer points to one or the other, but it doesn't intrinsically say which. So if I tell you that there's code at 0xDEAD, you don't know whether I'm talking about the one half of memory or the other. Also, you'll very rarely find a memory management unit. So the MMU tricks and disabling execution of particular regions or disabling writing, those don't really exist. The closest analog is that flash memory is rather hard to write because of physical issues, not because of any intended security defense. But these are still computers. You can write an exploit for them. You can run code on them. You can patch the code on them. You can even do multitasking operating systems if you can figure out how to fit it into available memory. So wireless sensors are the academic term for this sort of technology, which includes, yes, here we go. Thank you kindly. I'm having all sorts of X11 issues right now. So the wireless sensor is the academic model for smart grid devices, for next generation landmines, for all of these different applications of Zigbee technology. And the gist of it is that you have both a radio and a microcontroller on a small board with a battery. They use mesh networking to combine into a larger network that can share messages. And then traffic is to be intelligently rerouted. So if a battery is dying, you can just send traffic through another node. As your network ages and the batteries begin to die, you can add new units to it to extend its life. Or in the case of some specific applications, like the smart grid, you have a steady power source, so you don't really have to worry about battery life in the same way that you do with military and wildlife applications. So this is a blow-up of a traditional Zigbee node, the tiny node. This was used for managing geological research. So they would drill holes into the permafrost, throw these things in, have them network to one another, and then share temperature data, share all sorts of things by the radio at the same time that they stored it to an SD card. I step down a bit so that I can point. If you look at this screen here, you've got an external antenna on the left, you've got an interface board here in the middle, which combines the radio and the sensors and all of that stuff together. A long life lithium battery, an SD card adapter, and a coaxial cable. And this can stay in the field for months or perhaps even years, depending upon how its firmware runs. So 802.15.4 covers, is a standard for the lower levels, and that's technically what these chips should be called. Zigbee describes the upper layers of a particular industry standard for doing these sorts of things, but it's also used as slang to refer to the entire system. Then the MSP430 is a 16-bit microcontroller. The first generation radios were just a radio. They would talk to an MSP430 or another microcontroller by an SPI port. And the second generation ones are the ones that include a microcontroller internally. So that's it for the review. I think we should get to breaking some chips. So the first generation, from Chipcon and Ember, you had the 2420. And both firms offered the same chip under different brand names. The idea was that Ember would offer software on top of that. Then Chipcon was purchased by Texas Instruments, and Ember remained an independent company. So the two designs forked off from this point. And because this was just a radio, keys were sent by clear text from the CPU to the radio so that the radio could do hardware cryptography. The microcontroller itself is too slow to do sophisticated cryptography on its own. So because this was sent over a wire in the device, all you had to do was reset the device to make it load its keys again. You could stick some needles in and you could watch it. So it was, I presented this at S4 Miami with a couple of co-authors, and I'll be doing a workshop on this in DEF CON, but it's really simple and not terribly interesting because you're just packet sniffing a wire, and packet sniffing itself isn't that new. Once you've read that key, you're able to participate on the network and do all of these crazy things. This is a needle actually sticking into the board and watching it on a scope. Here you'll see the clock signals for 2 bytes being sent across. Data is written on the rising edge and it's read on the falling edge of this. And this is the data itself. It's sent most significant bit first. If you overlay the 2 on a dual trace oscilloscope, you can actually read it by hand. Or there is software and hardware from a company called Total Phase that does an excellent job of reading it for you. So then this came out. I got a couple of snotty comments on my blog, which I try to keep purely technical, like this one, saying that the Zigbee Smart Energy Profile uses secure communications, and the two aren't related, and he says the vast majority of pilots and products out there that support SEP, the Zigbee Smart Energy Profile, are based on the Ember EM250 and not the Chipcon 2420. Utilities are requiring the security and standardization that the SEP provides. So I looked up the datasheet for the EM250 because I've got to be fair to them. Perhaps there is some security to it. It uses a 12 megahertz XAP 2B core. This is an obscure chip from a consulting firm in England. They'll sell you the design, and then you can throw this into your own chip. So if you're trying to roll your own microcontroller device, you buy this, you throw it in, and then the microcontroller part of it is taken care of. You only have to worry about the radio. This is very advantageous to a company which has good analog engineers, but which does not have anyone experienced with designing computers. And of course, it also contains a radio internally. So the argument is that because the Chipcon is vulnerable and the EM250 does not expose keys in the same way, that it's secure. This is not true. The reason is that the XAP2 chip from Cambridge Associates has a JTAG port without a fuse. So most chips have JTAG for debugging. You can connect, you can reflash it, you can dump the contents of memory, you can read everything. But before the device is shipped in manufacturing, the manufacturer has the option of blowing a fuse to prevent you from having future access. The EM250 is programmed by 3 methods. These 2 are probably vulnerable, but I haven't had time to look. The JTAG debugger, however, This being the plug here in the photo to the right, having these pins is connected to by a debugger like this. And because it lacks a fuse, you can just purchase Ember's own tools and then load up the debugger and say, I would please like a copy of flash memory. And it will give it to you. And short of physically damaging the chip, there's nothing that you can do to prevent this. Because it's a surface mount chip, there aren't really any external pins that you might pull out. And there's nothing that you can do short of breaking these. There's nothing supported in the data sheet. But if you were trying to run through these by checkbox security, if your engineers told you that you need memory protection, reading the data sheet from this, it actually brags about its memory protection. But it's not in the sense of protecting from external access. It's in the sense of preventing your user application from accidentally overwriting the operating system, which consists of little more than a networking stack that Ember ships with these chips. So what was initially intended as a reliability feature was accidentally misadvertised as a security feature. So that's all that I have to say about the Ember. It's not that much fun to play with. But when I reported this, Ember is a really honest company. So they got back to me immediately and they said, yes, we have this problem, we know about it, we're working on it. They didn't try to dodge my email, they didn't pretend that the problem didn't exist. And it's rare to see honesty like that. So I figured I should look at the other chips in the market and break all of them. So the ChipCon 2430 is from Texas Instruments, which purchased ChipCon, the firm that used to collaborate with Ember in the first generation. It's a system on a chip, just as the Ember is, but it consists of an 8051 microcontroller, which is very, very distantly related to 8086. Debugging is done in an SPI-like framework. So you speak over a serial port, and in each session you send a command byte followed by some data bytes, and then you optionally receive a single reply byte. This is an example ChipCon device that a friend of mine in Slovenia made. Here in the center you have the chip, you've got a crystal for it and some other analog components. Debugging connectors are here, general I/O ports are here, but there's only the single chip. There's no need for an external microcontroller. This runs IPv6. So you can throw these throughout a building to do environmental monitoring or whatever you like, and actually give each one an individual IP address. And then if you have an IPv6 capable workstation, you can actually connect to them with regular networking tools. And because each is individually addressed, you don't have to worry about going through a proxy or a web interface for managing these things. The way that debugging works is that you first send an initialization sequence, and then you send a number of commands. This is a partial list of commands. You can erase the chip, you can get the program counter value, you can debug an instruction, which executes a CPU instruction. You can also get the chip ID, and then it will send a reply, you send another command, and you just sort of spin this way. There's a single data pin that reverses directions between commands. So if you send get chip ID, it's an input until after you sent that command, and then it becomes an output to send you back the reply. When implementing a debugger for this, you need to have a resistor between them so that your timing mistake doesn't actually create a short circuit between the two microcontrollers. So I built a debugger. This is the GoodFet. These are open source, and we've been giving away 180 of these over the past 2 days. I'm presently out, so don't try to grab any after I leave, but if you email me, I'll send you one for free. The board itself, not the chips. You have to do some soldering. So the GoodFet sends 2 clock pulses while the reset line, which is inverted, is low. So you sort of hold the chip in a reset state, you send 2 pulses, and then you let it run again. And it begins to accept debugging commands, whereas before it would not have. Debugging commands are sent in SPI. You've got your most significant bit first, all the way down to the least significant. data is written on the rising edge. So you see that this edge here is written at the same time that the 5 clock cycle begins, and then it's actually read during this edge by the other participant. They go by this particular framework, and there's a direction convention in that the master always speaks first, and then the slave replies. So there are different commands that you can set. Like you have 5 bits that describe an instruction, 1 bit that describes whether you are reading or writing. You've got 2 bits that describe how many bytes you're going to pass of data, followed by those object bytes and the return bytes. And then the chip has 2 states. There's a locked bit that you can set, so that if you're debugging it, you leave it unlocked, and you can run any debugging verb you like. You can tell it to show you the program counter, you can single step it, you can debug and skip, where you replace a single instruction in the existing code with an instruction of your own and then continue moving. When locked, you're only allowed to erase the chip, to read the status, or to get the chip ID. And the only way you can unlock the chip is to actually erase it. The idea here is that once you've erased the chip, there's nothing left for you to steal. So even though it's very easy to replace the firmware on one of these devices, it's very difficult to copy the firmware of this device. So if I buy your thermostat, it's very easy for me to load new code into it to run my own Hello World application. But I can't easily get a copy of your application to sell in copies of your product. So the chip erase function erases all of flash memory, all of firmware, including the debug lock fuse. But it doesn't erase RAM. And power is never lost from the chip. So if you run chip erase and then you dump out all of RAM, you get a clean copy of everything that was in RAM in the application at the instant that you erased it. On an MSP430, there's the same vulnerability. In the bootloader, the bottom 32 bytes of RAM are clobbered, but everything above that is protected. The difference is that the MSP430 is von Neumann, while the 8051 is Harvard. And Harvard architectures work differently, in that data memory is not executable, but it's faster to read it during, say, a move instruction. Not only is it faster, but your pointers have to be consistent. And C can't handle 2 different types of pointers, which are both integer, but which are not interchangeable. So the way it works is that because these pointers are incompatible, to manage this divided memory while still making the C programming language work, they have to copy things out. So all of the compilers will move variables, including constants, from flash memory into data memory, from code memory into data memory, from flash memory into RAM, leaving a copy of them to be taken. And this includes constants, because anything that might possibly have a pointer to it, which might be passed to a regular C function that expects a pointer in data memory, must exist in data memory. So at the very beginning of each application, there is a little routine that just copies a list of a large block of data from code memory into data memory. And this entire block is exposed to an attacker, because he can erase the chip and then he can read it out. So to do this, you just use the Goodfet client. You erase the chip, and then you write that output into a file. Then Joshua Wright is working on a tool called Killer Bee, which will be released at a later conference. It takes 2 seconds for this tool to identify a key in the upper half of RAM, and 4 seconds to identify it in all of RAM. Now, if it's a constant moved over by the compiler, it's automatically put in the top half of RAM, because this part is retained when the chip goes into a low power mode. As a power optimization or a bug or something, the lower half of RAM on this chip will slowly degrade when the chip is in a low power mode. So the compiler will never move a constant there. It might move a session key there, which is why the tool does either half or all of the region. So for the defense, they actually wrote an application note, ChipCon DN200, which now has a Texas Instruments name that I forgot the code for. And they basically suggest that you use this __ code keyword to specify that you want the string list foo to be placed in code memory instead of in data memory. The problem is that if you do this, you can't call printf on it, because printf expects a pointer to data memory, which means that you have to rewrite your networking library such that it never keeps the entire key in RAM at once. So in DN200, they suggest copying it onto the stack as a way of reducing the amount of heap memory that needs to be used. Or by heap, I actually mean global memory, because a heap is rather rare on a chip with as little RAM as this. And that works as a performance optimization, which is the spirit of DN200, but it doesn't work for security reasons, because until that space of the stack gets clobbered, it still exists in RAM to be excised. So all currently available chips are vulnerable to this attack. The upcoming 300 series chips are not expected to be vulnerable to this particular attack, but I've yet to see one, so I don't know what else might be in store. Protecting against this is possible, but it requires some recoding. You're going to have to change your firmware. And part of the reason that I'm here today is that no notice was sent to users of this chip suggesting that they patch their code. There is some work going on in changing the chip so that later revisions of certain models will do a RAM test, which clobbers all of RAM before they actually perform the erasure. But if you're using this chip, go back through these slides, go back through the article that I wrote, and fix your code. Because it's not insurmountable. Because the default C compiler moves it over, however, all existing chips are vulnerable. Now, the EM300 series will have a JTAG pin fuse. The ChipCon 430, which is another of the third generation chips, which is not yet available in quantity, it uses an MSP430 microcontroller and has a JTAG tap fuse. But both of these are soft fuses, which makes me a bit nervous, because when the chip has erratic power, it sometimes misreads from flash memory, especially if the flash memory is written at one voltage and then read at another. A guy by the name of Sergei Skorobogatov did a lot of work on this, where he would write an image in at one voltage, then change the voltage and read it out, or blank it out again. And neither of these chips is yet available for products. So this is the 300. So to conclude this section, the Zigbee chips that are presently available are not secure to local attack. They have vulnerabilities in the way that they're debugged. You can connect to them, you can rip out their keys, and it's not very difficult. The next generations might be better, or they might not be. I don't know until I see the chip. And local security is really hard. Because when I'm attacking your device locally, and I have it in my lab, and I can do all sorts of nasty things to it. I can stick pins into it. I can take it apart. I can do anything I like, even including chemistry when necessary. And the software security world generally hasn't had to worry about these things. When you're worried about an attack, you're wondering what happens when someone comes in over the network. And our industry understands very well how to find mistakes in networking code. But in hardware, there are very few places you can go with a chip to say, hey, is this debugging standard secure? exactly how hard is it to rip the code out of this device. There are a few firms, FlyLogic Engineering being one of them, but not many. So for my second part, I'm going to discuss rootkits for these platforms, and just a few neat little tricks that might be used to make them smaller or more agile, as well as ways to identify them. And Mike in the back might, it'll be interesting in a couple of hours to see exactly how many of these recognition techniques would actually find your worm. So inside of a rootkit, you use interrupt vector table proxying and hooking to relay the initial interrupts back to your own code. So first your code is called when, say, a byte comes in through a serial port or when the chip turns on, and then it passes control back to the original code. You can forward as many or as few of these as you like, but for the sake of this discussion, I'm going to assume that you proxy all of them. It's also useful to have blind command reception. So if you're designing a rootkit for a particular hardware device and you don't know what the firmware will look like, you might not know which version is present, or you might not have time during the installation to patch it. You can do blind command reception. So you can actually have a rootkit that knows nothing of the application that the device is intended to run and takes a little performance hit to identify commands anyways. You can also do efficient command frames and efficient parsing of them. So if I were to do like an XML parser, that would take a lot of space inside of this firmware image, and that space can rarely be afforded. You've got a 16-bit chip, 65 kilobytes of memory, maybe 50 of that will be flash memory. So in 50 kilobytes, you have to have both the original application and your operating system that forces itself on top of that application. And you need to do blind function calling sometimes. So if I know that there's a command that sends a packet out of the radio, it might be easier to find that command and call it than to include my own copy of that command. So in 2007, I wrote the first exploit of a wireless sensor worm, and then in 2008, I came up with a reverse engineering toolkit that allows me to parse and view the individual images, and that's where the diagrams that you'll see here come from. And then in 2009, Davis's worm has been written. You can catch his talk at 4:45 in this room. His implementation is practical, which mine is not. I'm here to show you what a worm will look like. I'm here to show neat tricks that might be used in writing one. My purpose is not to have one on a particular device or anything like that. So because memory is precious and there's no operating system, you have to be small and you have to create your own operating system. There are no system calls or function tables or similar things that you would hook on a PC. It's not as if you can do an interrupt to the operating system to do anything. It's not as if you can ask a DLL's header for the function names, because those things don't exist. There's just a single statically linked image. And code is in Flash, not RAM. So it's rather difficult to rewrite existing code. If the image is nearly full, you can't just move the interrupt vector table and then rewrite it. You have to move it down to a lower segment, erase the top segment of flash memory to all ones, and then clear the bits that you want to leave as zeros. So the overwriting becomes difficult. Generic installation is useful, and you want it to coexist with the prior firmware. You also want it to fit in just that slack space between the top of the prior application and the top of available memory. And you want to reuse the existing code, and you can do a memory security trade-off because you've already infected. It's rather rare that something else will be trying to attack the same system. So you can just run executable code when a packet comes in. You could never do that in a regular application securely, but when writing the worm, you might not care. So the MSP430 itself is 16-bit with a couple of 20-bit variants. It has a bootloader and masked ROM, and this is the only code that you can be guaranteed will exist on the system. I have a paper coming out at Usenix next week where I actually trampoline into that to extract the firmware using a blind stack overflow. And I've chosen this for a concrete example, not to pick on the MSP430. So how do you find a function without linking tables? What you can do is you can actually identify the beginning of a function, because that's where an immediate call will go to. So in the disassembly, you'll see call followed by a 4-nibble hexadecimal address. Call 0x4000 would call the very beginning of flash memory on one of these chips. And almost every function is called that way. Function pointers and things that you might expect in a C++ application are very rare here. So you can just scan all of memory for these call instructions. And they're all 2 words long. The first word is the call instruction itself, and the second word is the address. So they're very easy to locate. You can just have a sliding window, compare, and then whenever you see one of those, you can scan the code after it until you find the last return after a relative jump. Okay, that gives you a block of code which is the code as it exists in the image, and you can fingerprint that. You can fingerprint it by saying, I want the function that matches this signature exactly. Or you could do it differently. You could say, I want the function that touches this I/O port. Because when performing I/O on this chip, you just write to a particular address. You don't have to call an operating system. You don't necessarily call a library, because you are the library. You are the operating system. There is no privilege separation. There's no user kernel mode difference. There's just the one environment. And then how do you make it stealthy? And is this even necessary? Is anyone watching? Is anyone trying to identify whether a rootkit has been found? So we've covered locating a function and the I/O ports. As far as interrupt handling goes, you've got a list of interrupt handler addresses at the very end of flash memory. Because this is flash memory, you can't just change an individual word of it. You've got to copy everything out and then move it back. You have to set up the writing of flash memory, and it takes a bit of code. Once you've done that, you can proxy individual commands by just having a branch to the original address. So if you move the whole interrupt vector table down, that's the data, not where the table itself resides, then you can jump to each target, and then it will return from the interrupt because it's already an interrupt handler. It always uses the ret_i instruction instead of the ret instruction. And then if at any point in time you want to do anything before the official handler does it, you're free to. So supposing that the device receives a packet, handles it, and goes to sleep, you might have enough time between when it wakes up and when it begins talking to the radio to scan the previous packet. In that time, you can see if it's intended for you, and if so, you handle it, you run its command, you run executable code in it, you do those things, while the original application just drops it as garbage and says, this key doesn't match, I'm not interpreting it. This is what interrupt proxying looks like. You've got a large application here in lower flash memory. Here, red indicates executable code. This sort of gray staticky part represents non-executable data. And it's interspaced with red because sometimes you have data that looks as if it might be an instruction. Then this black region is all FFFF, all unwritten flash memory. When flash memory is cleared, it becomes all ones. Then at the top, there's this tiny little green space up here, which is the interrupt table itself. And whereas it would usually point to the lower applications, instead it points to this upper one, this red bar at the top. If it were not proxied, it might look like this. And the black at the top is cut out because this comes straight from a compiler instead of from a chip. But you've got just the green with no red around it, and then all of these addresses in the green will point down to the red here. Furthermore, the very last one, this is the top right, always points to the very beginning of flash memory by every compiler. And you can graph them. You can make like a graph theory directed graph, whereby every vertex is a function and every edge is a function call. And if you do this, and the two aren't built for one another, the code at the top, this here, never makes any calls to the code at the bottom. Between here, there are no lines. So it's very clear from this diagram that there are two applications here and not one. And if you do things like searching for functions in the lower image, they won't show up here because this only shows regular literal calls. It doesn't show a search that returns a pointer or a function pointer call or any of those things. Here on the right, this circle of handlers, or the circle of functions that go nowhere, those branch to the original interrupt handler. Except for this one, the reset vector, which runs off into the other code. So you can see which are simply passed over and which ones are handled. If you zoom in here, you can actually read the address, grab that function, and begin to see what it does. In this case, it's an innocuous bootloader. So you might get a false positive with this method, but if you know that no bootloader exists, or if you know that no bootloader is intended to be in the project, or if you compare different versions of the same product, then the presence of this when it shouldn't be here would indicate a rootkit. In any case, you've got this sliver of code at the top of memory to analyze instead of the entire massive application. And moving this code is rather difficult because you have to make sure that all of the absolute offsets change as well. And so far as I know, there's no tool that does that on this platform yet. So it's also used without malice. It's not necessarily indicative of something malicious. But it drastically changes what the bootloader password is, because that interrupt table at the top is how the MSP430 controls your access to it. So if you're trying to read the contents of memory out through a serial port, and the thing has been Trojaned by this technique, you don't know what the bootloader password is. So then you find yourself locked out of your own device and unable to verify its software. And you can do tricks like comparing the bootloader password and the call graph and the memory usage and the calling conventions to identify this. If the two, so we've been over the bootloader password and the call graph. The memory usage is important because flash grows down from the top of memory. If you've got 4 kilobytes of flash, it will always end at the top of memory, just as 8 kilobytes of flash will. The code grows from a starting address upward. So every compiler generates applications on segment boundaries. And that segment boundary is always either the one of that chip or another chip in the same form factor, if you're swapping them out. The GoodFet firmware begins a little high. But if code begins anywhere else, then you know that there's an issue. And a worm will also go from a segment address because it doesn't want to waste, whoa, apologize for that. It doesn't want to waste any space. So it has to grow upward from a segment boundary. The calling convention is another way to do it. Hackers use GCC. All of my products are made with GCC. The GoodFet comes with GCC. All of its code comes compiled by it. So registers are used, register 15, then 14, then 13, then 12. But commercially, most of the developers use the IR compiler. IR has two conventions. Until version 4, it would use register 12 and 14. Register 13 and 15 would go nearly unused unless you had code that required a 32-bit value. Other compilers follow still other conventions, and you'll also see differences in switch statements, and I've documented all of this online, so you can look at an image and you can tell very quickly which compilers made which regions of it. If I'm writing a worm, I get fed up with IR rather quickly. It's not easy to use from the command line. It has licensing restrictions. It has all of this stuff. So I'll use GCC, and if I'm targeting a device that's made with IR, you can compare the two, see that two different compilers were made, and then figure that perhaps different authors wrote the different regions. You can also fingerprint on switching on the assembler even. There's one compiler which misassembles a move of a -1, or anything that uses -1 as a source. And instead of compiling it as a single word, it compiles it as two because it forgets to use a constant generator. There are also unused interrupts. Do they all point to one address, or do they have separate handlers for each? This is a list of two interrupt vector tables. On the left here, you see that they're all in high memory. FB78, FB7C. Everything begins with FB. So they're all in this one small little region, beginning maybe around FB00. In this case, it actually begins at F800, which you see in the very last interrupt. But the interrupt table on the right is very different because 403A exists very many times. This is a default handler, and it's generated by GCC because GCC wants to make sure that whenever an interrupt is fired, even if it does nothing, it's at least handled by something so that the chip doesn't crash. And then the only other ones found are those that are actually used. So if you use, say, a brownout timer interrupt or things like that, then you have a handler to something else. IR would make these FFFF instead. And then the very last one points to 4000 here and 5800 in the other, because all compilers for this platform target the very lowest address of the space that they're given as their entry point. So you can see that this is in high memory on the left, and this is in lower memory on the right. If you know that the chip has memory beginning at 4000, you can see that this one is native and that this one has a second application added onto it, either a rootkit or a worm or a bootloader. So to conclude all of this crazy stuff, Zigbee chips are not locally secure. Not one Zigbee chip that you can buy. The accepted vendors will, I need to contact them before I publish those vulnerabilities. And the next generation will likely be broken too. The chances that you can have local access to a device in your own lab with your own wiring, with a soldering iron, and not be able to break it, while at the same time not significantly increasing its cost, are rather slim. How much is it worth to you to make sure that I don't change the code on your thermostat? How much is it worth to your customer that I don't change code on the thermostat that you manufacture? And they'll all say that they want security, but very few of them are actually willing to choose your product over your competitors because of it. And until that changes, this code will not be secure, and these devices will not be secure. And then while embedded malware is easy to write, because no one is looking for it, obfuscation techniques are not necessary. And because they're not necessary, they're not used. And when they're not used, it's actually rather easy to recognize malware once you have a firmware dump. And then these same vulnerabilities that expose the chip initially might actually help you to run forensics and to determine whether a device has been tampered with later. So while it's terribly inconvenient if you're trying to protect your firmware that the Ember chip does not defend it, if you think that it might have been infected by a worm and you're trying to get a copy of that or to figure out exactly what went wrong in the field, it suddenly becomes useful because then you can rip out memory and you can look at it. So do you have any questions? None at all. Oh, yes? Okay, so the question was, how does this apply to manufacturing technology? Like manufacturing plants that previously used older SCADA equipment. The older SCADA equipment was very often wired. And the argument against really securing those protocols was that it's on a wire, someone is going to have to come into my plant to attack me, they're going to have to plug into that wire, participate in this network, and by that point they could just throw a wrench into a machine and save themselves a lot of trouble. In switching to wireless, you wind up with protocols that are more secure. ISA 100 and I think Zigbee also has a manufacturing standard. They're ensuring that at least some cryptography is used. They're making the protocols themselves better than the wired equivalents. But if you're being attacked, you still have the situation that a wrench might be easier. So in manufacturing, I don't think that you have to worry so much about sabotage in that your machines might be used against you to damage themselves. Instead, you have to worry about espionage. Can your competitor tell how many widgets you're pumping out just by listening for the radio signal that your factory broadcasts? And that would be interesting to look at. If you have any industrial Zigbee equipment, I would be happy to look at it. Yes?
So when you have something that's got a malware rootkit or something like that, somebody's announced it's there, that's going to modify the error vector table, error vector table. So, I mean, are there expected to have DSL cracker or other tables to be able to get access to code?
Well, sure. 180 people in Vegas have one now, and
Give us the chip, man.
I gave you one. Oh, you mean for soldering? Yeah. You can order them. It's a free sample from Texas Instruments. They're very neighborly. And then you can use that to break right back into MSP 430s. So, not yet. But all of the technique is in my article from the Congress in Berlin. So. And voltage glitching is actually a lot faster than BSL cracking and works on more versions of the chip. Yes, many more chips. One of the experiments that I'm about to run is on glitching JTAG. So now that I've got a JTAG debugger of my own that I control all of the code of and that I can modify in crazy ways, I can drop the voltage and bring it right back up at the instant that the JTAG state machine goes from its power on state to the state where it checks the fuse. So then you've got one number being incremented and then held in a register for use later and on the next clock cycle to determine where it is in the state machine. If you glitch at that moment, the number will be wrong. And usually you only have as many bits in this number as you actually need for your states. How the other states are handled varies by the way the VHDL was written, but if you find yourself in any valid state in a JTAG state machine, it's a very simple problem to navigate back to the beginning. You just hold a line high for a bit, then twiddle the clock, hold it low for a bit, then twiddle the clock, and you find yourself back ready to populate the address and data registers as if you had passed the fuse check. You can also do the same thing as an instruction is being latched in. And in doing that, you can make the wrong instruction be latched in. So you can do a sort of skip, either for the instruction itself or for the data that the instruction reads. All sorts of fun stuff. Yes? Neighborliness abounds. So I've got the equipment with me, but it's a bit hard for me to see the screens at once. So if you'd like, and you're done with questions, I can plug it up and demonstrate it. I understand that live demos are boring, so I won't be offended if you decide to leave now. Okay. Can everyone read the text on the terminal? You can? All right. So I've got this here, which consists of a GoodFed 11. GoodFed 20s are being distributed here at NeighborCon and at DEF CON. When you have one, you just assemble it by soldering the surface mount components on, and then firmware is actually flashed in through Linux. This appears as a serial port to your computer. You say make install, and that flashes the firmware. And then you call a client, which can be written in Python or any other language of your choice. On the other end, I've got a ChipCon 2430 mote, which has been wired up on the proper 16-bit cable. So I connect it in, and then I can call goodfet.cc info. Okay, and this identifies the chip number. So as you can see on the top left, I'm using ChipCon 2430 of the 4th revision. There's also a status register that tells me whether I'm locked out or things like that. So I've got the script here, which you'll find on your Black Hat CD. And if we read the script for a bit, you see that at the beginning, it explains itself. Following that, it goes through 5 stages. In the first, it writes something that is not random into data memory. So I'd populate RAM with something. Then in the second stage, it dumps it back out. And in this case, I'm doing 32 bytes at a time because that's sufficient to demonstrate the technique. There's no sense making you wait for all of flash memory to be dumped, or all of RAM to be dumped. Following that, all of memory is erased. And then that same region of data is read again. So you wind up with 2 files, foo.hex and bar.hex, each of which should be identical to each other if RAM was not erased. If RAM is changed in any way, then their checksums will differ as compared in stage 5. Okay, so here it writes something into memory, then it dumps it back out, it erases it, it dumps it a second time, and you can see that the checksums match. If I cat foo.hex, you can see that, and I also tail app.hex, you can see that the data is the same. App.hex is a little bit extra that wasn't loaded into the chip, but it's the first 2 rows that are relevant. And you can see in these, here that like 403A, 403A, 403A. That's because I copied the MSP430 image from the prior example in. So to extract keys, instead of dumping the limited range, you would just dump everything. And then having dumped everything, you try every window of the appropriate key width to decrypt packets until the decrypted form has very little entropy, indicating that it's clear text. Then you verify that, then you load this into your packet sniffer, and then you can view packets in the clear. And as I said before, Joshua Wright will be releasing the tool for actually examining these at a later conference. So, thank you, and have a good day.